Hello, Space Cadets! It's your old pal Vector Spaceman back at it again. We're coming to you live once more from Harbor Station, broadcasting on all frequencies to our beautiful planet Earth. Now, whether you're watching us live or catching us after the show, don't you know that we're glad to have you on board. Thanks for helping us make outer space the place to be. It's Tuesday, May 24th, 2022. Welcome back, one and all Space Cadets, new viewers, and of course, if it's your very first time tuning in tonight, then hey, welcome aboard. I'm your host, Vector Spaceman, and this is our little old Vector Spaceman show. We're back to proper streaming this week, bringing you a number of shows over the next few days, evenings as it were, along with some friends of the show as we stage a proper return to form, having made some pretty great strides in the development of our updated live 2D model over the past couple of weeks. It won't be long now before we get to see it up on the big screen. Stay tuned for that. If you missed the last show, we spent our lazy Sunday afternoon together puzzling through some quizzical and curious challenges with the text-based game board puzzle game Baba Is You. We opened up a whole new zone, which is fantastic, but at the same time, means we're still not as close as I had thought to finishing up that game. No matter, we've got what it takes. And even though we've been revisiting it on and off for months now, ever since we first started streaming, we'll keep chipping away at it, at what may become our greatest triumph ever here on the show, finally finding a way to beat that game. And of course, if you want to stay up to date with all of our broadcasts so that you never miss a show, then be sure to follow Vector Spaceman on Twitter, YouTube, and right here on Twitch. As for tonight, Space Cadets, it's time for a different sort of puzzle, as it were. One that promises to teach us a thing or two about the world of programming and machine learning. A bit of edutainment, if you will. A bold strategy trying to sneak learning into one's game time, but after our first experience with this title last week, I've actually had a good bit of fun so far. We are returning tonight to While True Learn, continuing on our quest to build a cat-to-speech translator while tackling some visual programming challenges and getting a beginner's glimpse into the world of AI and machine learning. Fun stuff, fun stuff. Even though I've got some, a little bit of experience with computer science and programming and what have you, I find it interesting looking at the way that we teach programming has developed over the years. Because I've said before, back in when I was in high school and university, taking my programming courses and what have you, it would always be given to us, taught to us, in a very rote way, very by the book, very, I don't know if you'd call it stale, but teaching it like a language almost. These are your set functions and things like this, but nowadays, what seems to be the thing to do is to sort of visualize it a lot better. You see a lot more visual programming introduced into, I know that they've got visual programming environments for popular game platforms like Unity or Unreal Engine, stuff like that. And I've even got friends who are involved in teaching, and when they have to teach concepts like this to young students, they lay out stuff like flashcards, make it very, make it sort of flow, make it more visual, as it were. And I think that's a great idea. And this game that we're playing tonight sort of takes the same approach. After our first playthrough last week, we got ourselves locked into some sort of scenario where data transfer stopped calculating properly. We must have spent 15 or 20 minutes trying to optimize our solution, only to delete everything, start over, and have it actually start working for some reason. But that's software development for you, though, isn't it? There's always some bug in the mix, I suppose. On the whole, though, it's been a great game so far, and I'm eager to get back into it. So, without further ado, we've got no big announcements or super special streams to hype this week, so let's get right into things. Let's get comfortable, get prepped, turn on your brains, and get set to think differently as we be programming geniuses in While True Learn. Let's head on over to the big screen. Alrighty, we're picking up right where we left off, which I think was right after the sort of first beginner module here that we got finished with. The first steps, as it were. So now we're on to Rosenblatt Perceptron. I like how this game always gives you like links to discords and forums and resources, so if you really want to learn more about these concepts, you can do so as well. Alright, we're getting more emails here from Cat Overflow instead of Stack Overflow. Nice. I don't know if I noticed that last time. Hey, so I've managed to make my computer detect the cat, but that beast is a complicated soul. Definitely has more to tell. Maybe it's time to go next level and start recognizing emotions. Cat emotions, eh? Ever heard of perceptrons? They were invented in the 60s to recognize written text. Everyone knows that everything invented in the 60s is awesome by default. True, true. The double helix, rock and roll, lava lamps. Also, you can maybe switch to dogs instead of cats. Decision trees work like magic for my Pluto. You can also hit the store and get that random forest node. A forest is more effective than just one tree. Alright, are we gonna have to pick up stuff from the in-game store? What does they mean by that? Error rate. And now for something completely different. Perceptrons can actually learn and improve. Bad news, they also make a ton of errors on the way. The percentage of errors is shown in this icon. Okay. So we got speed and we got error percentage. Use training mode to teach perceptrons and decrease the amount of errors. Ah. Mark 1 perceptron. In training mode, reduces the amount of errors while trying to predict the shape of elements. Ah. In test run, only predicts shapes. In the real world, Rosenblatt's perceptron used in Mark 1, this perceptron could recognize only simple dependencies. But it was enough to recognize English letters. Oh, I see. So that would have been, you know, very early stuff like scan to text or something like that, right? Cool stuff, cool stuff. All right, what's the design here? We got our inputs. Circles go here, squares go here, triangles go here, and we want to train it. Full speed. Get our error rate down to what exactly? What counts as good? 20%, I guess? The nodes on the field have reached their minimum margin of error. Nothing more you can teach them. All right, then let's give it a test run. Hey, nice. So I guess this value here, the 60%, we got to keep these above that percentage of accuracy. Okay. When we're given tasks and stuff. So now we can work on some problems. Let's see. We're getting a little email here. Dairy product manufacturer. Hello, my name is Sam. I own a dairy product factory. My dream is to make the very best goods on the market, and that's impossible without high accuracy in fermentation processes. Sounds legit? All right, off with the fancy words. I want a program that would judge the quality of a product by its ingredients. We often make mistakes, and a lot of our products never leave the factory since we mark them as defective. We have the data, but we need the algorithm. All right. We can use up to 2 nodes here. Output stream 1, output stream 2. What is the idea here, though? Why do we have stream 1 and stream 3? All right, we got our inputs coming in. That's fine. Can these go to multiple? They cannot go to multiple outputs. This can take any though, so maybe we put squares and triangles up in here, circles down here where only circles are allowed to go. Don't bother with a trash can. Let's train our system. All right. We've got good accuracy so far. Let's give it a test. As long as those both hold above 40% accuracy, we should be good. Ah, but we only got bronze? Why is that? Why is that? Because we went over our time limit? Let's edit our scheme. Surely we can do better, right? Surely we can do better. Gotta get it done in 39 seconds. Was it just a matter of bad RNG? Let's give it another go here. No, we always go under because we always get the same data set. Alright, well, they're letting us use 2 nodes, so let's bring in another perceptron. Trash cans do count as 1. Yes, they do. Alright, so we're not going to do that. Can we... I mean, what happens if we have these in series? Does that make it any faster at all? Surely it shouldn't. Why give us the option for the trash can, though? What do we need that for? Should we be ditching some of these, I wonder? How many do we need? We need 30 to wind up in here. We need 10 to wind up down here. If we just ditched triangles... Does that change the speed of anything at all, just because we have more paths at this point? Surely it wouldn't, right? No, in fact, it seems like it's much slower. Ran out of time. Bizarre. What are we throwing out then? Or what would we use a second one of these for? Here's how we had it set up before. I'll train our scheme here. Everything seems to be working. Drain the whole input stream. Give it a test run. Should be just over the time limit if the same thing is occurring. Yep, tips right over. So how do we optimize this then? Get some info here. Nothing seems to help us. However, we might save some time. I actually don't know if this would save any time. We can always double check parts of these. Get that down to 20%. Seems arbitrary to have us do this every time. Or maybe we should be double checking the circles. We'll see if this turns out to be slower. Give it a test run. Here we go. we're getting held back because this one's taking too long to fill up. So we shouldn't be double checking that one, and it shows here. Ran out of time. So what we should be doing sending these straight to the source, double checking the circles, just in case anything gets lost. Let's give that one a go. Running out of time because not enough data is making it into stream 1 by the time the time limit comes through. But here we go. Yeah, there we go. Gold star. Nailed it. Release. Ship it. Get some more cat euros. Don't mind if I do. Metal Gear construction. Hold on. Hello, we are the Metal Gear Construction Factory. We produce fittings and supply... Oh, that's less interesting. Raw materials to construction grounds all around the world. We are especially proud of our high standards of quality. At the moment, we're receiving a lot of new orders, and we are running late with the deadline. An algorithm is required that will analyze the quality of raw material and discard poor quality ore before it leaves the conveyor. Seems like a good real-world application. Manual analysis takes way more time than we can afford, which is why you have to call upon Spaceman. Oh wow, they're going to let us use up to 7 nodes on this one. Okay, so now we're combining color trees with perceptrons, and maybe even a trash can. We'll see if we need that. So we only want red circles and squares, and only blue and green triangles. Very good, very good. So here's where we might actually make use of a trash can then. Okay. So first thing I guess we'll do is color tree. We need 2 color trees in order to separate reds from blues from greens. So we'll say a blue and green, because that'll filter red through either or. Red, blue, red, green. This may not be the fastest, but we'll compare speed once we actually get a working prototype going here. And if we wanted to, yeah, that would max out all of our nodes. Plus we want more emphasis on red, I think, so that probably works. Okay, so red circles, red squares, green, or no, red triangles go into the trash. Circle trash, triangle. Output, and same here. Because this is going to be our red comparison. This will be our blue, and this will be our green. All right, let's train it up. See how it flows. All right, we are just slightly above the margin of error, it looks like. All right. Let's give it a test run. We got to fill that up in 28 seconds. Let it flow. Here we go. There is something satisfying. about seeing the data nodes performing. Okay, we are quickly running out of time here. Looks like we're going to make bronze. 94% accuracy, that's not bad. Surely we can do better, though. I think we should probably be doing a perceptron first, perhaps. Let's see if that makes a difference. So we can already filter all circles and all squares into its own tree here. So we're kind of just going to do the opposite, I think, of what we did before. More color trees, which are faster to process, and fewer perceptrons. I think we can get away with just one. Plus, the color trees are, like, super good at what they do. They'll be able to weed out trash a lot better than the perceptrons could. So we want reds. We want green and blue, because red will pass through both. We might even be able to, let's see, green and red. We only need 35 of these data points to actually get through. We just waste half of them? Nah. No, we probably need more than that. Let's see what happens if we do. Meanwhile, green, blue. Blue, blue. Here we'll actually do a proper color tree. So green triangle, of course, goes here, blue goes here, the red goes to the trash. All right, let's train that up. And we're still getting, oh, failed their minimum margin of error. Oh, have reached their minimum margin of error. All right, let's test run then. We're kind of skipping around the 60% accuracy mark there. All right, we're not gonna make it. No, look at that. I think we're gonna run out of time on this one. Tisk. All right, that was even worse than our first one. Gotta rethink these color nodes here. Okay, all circles. All triangles. We got 40 triangles in this mix. So you would think that having just all of those get through would be enough, right? Are we quick enough to calculate all of that, though, is the question. That's the question. So that's going to send through blue and green. So why even compare blue and green at that point, right? Right? Because blue and green, we can take both. That's no problem. Red and green, we just need one more comparison for that. The red ones go to the trash. Green ones go in here. We send everything else to the trash. I don't think this would make it in time, but theoretically, this is all that we would actually need. We just run out of time for it. Because there's no telling at what point, like, all these blue triangles actually come through the dataset. Which means we need to send more red stuff into here. With 2 more decision trees, I think is all that we would need. That would send red and green, that would send blue and green. The blue and green can go straight to the bin. If the reds go here, blue goes to the trash as well. Give that a test run. Now we should have more nodes making it to the end zone, but I still think we're going to run out of time here. We're definitely running out of time for gold again. I guess the smarter thing to do was the color separators at the very start. They're quicker to perform, and so they send more data out faster. So let's see if we can't optimize our original design then. Alright, red and blue, green and blue. So at that point we only need one perceptron for that one. Because blue and green goes in here. Blue and green triangles go straight here. Everything else gets binned. Meanwhile, red and green. Let me send all the red stuff through here. That's fine, that's fine. All the green stuff straight to the bin. Like this, yeah? That's pretty efficient use of node that only used 5 out of our 7 nodes. Let's train it up. Are we getting better data flow for that? Let's see. Looks like we're getting some backup down here. Some stoppage. Alright, test run. Let's see how it do. Alright, filling up. Fairly quick. Ah, no, see, we're overflowing again. Are we even going to make it to bronze? We ran out of time. How is this worse than our first design? Seems we are getting data piling up. So turning this into blue and green. how's this? This looks a lot like our original one, I think. Gonna have to train it again. Slight data backup here, but looks like we're okay. Hey, Dragon! Yo, Spaceman, how goes the brain game? Oh, our brain's just too big. Too big for this game. We're about to do another test run of our latest design. Sorting colors and shapes. We're stepping up in the world. Let's give it a go here. See if we can't make everything go where it's supposed to in a timely manner in the next 10 seconds. Come on, can we fill up this bar? Can we fill up bars? Nope, we're rolling over into bronze medal territory. Can we even finish this one in time? No, so again, actually less efficient than our very first design. How are things going with you though, Dragon? Did you have a nice weekend? A nice Monday, I suppose? I always forget that we miss the first day of the week. We rarely broadcast on Mondays, but I hope everything's been going well for you. Here's what I'm going to try next. Another Perceptron. We'll have one for each individual color. We'll see if that one works. Weekend was good. Monday was good. I've been feeling a bit fatigued, but streaming good times. That's good to hear. Don't wear yourself out too much. Maybe you've got that new monkeypox that's going around. Be on the lookout. How's the Spaceman been? Just fine, just fine. Had a nice little family dinner the other night with the Vector Space fam. Always good to visit. And you know, I've been saying I've been out enjoying the weather every chance that I get. Biking, hiking, just being outdoors. We do love this time of year. Alright, so red, circles, squares, yes. Everything else, bin. Blue, triangles. Everything else, bin. Green, same deal. Triangles, everything else, bin. Train it up. See how it goes. This may be optimal design right here. We're getting a little data backup on the blue one. See how that affects the overall performance. Oh, looks like we're doing a little better. We might actually finish this one in time. Look at that. Bronze star. But surely we can do better. Right, right? How often do you get Space Fam time? Oh, maybe once every couple of weeks or something like that. We'll all get together. Gotta request time off when you're stuck up here at the station. Nice, though, that they're not that far away. All things considered, relatively, I suppose. In the grand sense of things, against the backdrop of space. What up, Spaceman? How you doing today? Mr. and Mrs. Pups, why thank you for tuning in. I hope you're doing well. We're doing okay. We're just trying to optimize some programming schema here. I know folks who see fam every week. I don't know how they do it. Think they might get a little burnt out from overexposure. It's possible. It's possible. Ah, yes, the coding school, indeed. Welcome to school. Professor Spaceman presiding. We've managed to bronze star this one here. But I'm not sure how we can optimize any further without getting some significant, like, backlog of data transfer here. And how are the pups doing? Hope you're both having a good day, good evening, wherever you might be in the world. See, the only thing I can think of is, why do we need to separate green and blue when we're sending through green and blue triangles anyways? They can just both go here. Would that save us any time? Let's take a look. Oh, not bad. Still overflowing though. I feel like that was a little quicker than our last design. Now technically we just need to keep our accuracy above 60% here, so I wonder if we can scam it a bit by injecting some purposeful false data. Let's do another test run, see what gets trash canned first. Blue squares, blue and green squares. A lot of squares here. Doing good, just chilling for now, nothing too exciting. You know what? I understand. I get that. That happens. How about us? Same sort of dealio. You know, it's just a lovely Tuesday evening in May. Kicking back, sitting around, chit-chatting with viewers. Trying to make our coding schemes a little better. Here's what I think we're going to do. We're going to try this. We are going to purposefully let green squares go through. Even though they're not supposed to be in there, I think that our accuracy will be fine, and we'll get our occupancy filled up before the time limit goes over, in which case we might gold star this. Let's give it another run. We just gotta keep this bar above 60%. Come on, 3, 2, 1. Oh, we were so close. We were so close. This game reminds me of Spaceman. Know that one? I don't know that one. I wouldn't be surprised if it's got similar developers, though. I just found out these guys make some other sort of learning, educational, edutainment sort of games. Prefer this one's aesthetic, though. Simple? It is simple. It reminds me a lot of the visual scripting IDE. I don't even know if you can call it an IDE. In software like Unity or Unreal Engine. I've been saying there's been a noticeable push towards teaching in sort of a visual programming style. Okay, we were able to get green squares through. What happens if we let blue circles through as well? Or is that going to overload our accuracy? Let's find out. Yo, gold star! 65%. So we've traded. Why is this the way that they... Why would they do this? Why would this be the way to win it? By purposefully lowering your accuracy just to make it faster. Are they trying to teach us something about the software development world? That sometimes you just have to cheese it? That sometimes you just have to sacrifice accuracy for efficiency in order to get something that's good enough? Like, is that what they're telling us? That the real key to victory in programming is building something that's good enough. Is that all that it is? Man, I remember back when I was taking computer science courses, when I was learning to program and stuff like that, like they'd always drill into our heads, like, you know, prioritize, you know, good coding, clean design, you know, don't use more memory than you gotta, you know, be efficient with all your design and all this. And nowadays you just got, everybody's got 128 gigs of RAM or whatever, 10 petabytes of memory. Or in the gaming industry, releasing an unfinished product, it's all good, we'll patch it. Isn't that the worst though? Day one patches that are half the size of the base game. It's called meeting a deadline. Yeah, spaghetti code. Ugh. Well, we're gonna ship it. Look at that. We're just rolling in the cat euros at this point. Oh, we got new jobs. Toy manufacturing. Howdy. I'm contacting you on behalf of Nuka Toy Company. We design and manufacture toys for children using 3D printing technology. Ah. CICD is great on concept, left so for quality. You know what this reminds me? I still gotta buy myself some 3D printing gear. That's something that I've been trying to get into for the longest time. Continuous implementation, continuous development. Yeah, the live service, as it were. The ongoing. Yeah, I get you. There are 3 types of raw materials we use for printing, and we need an algorithm that would distribute them correctly. Passing a certain errors threshold could result in a disaster. What would I make with the 3D printing stuff? I'm not sure. I'm not entirely sure. I'd probably use it to sort of jumpstart making the Spaceman 3D model, the Spaceman 3.0. That's been something I've been wanting to do for a while now. I have heard that you gotta have some pretty good, like, ventilation, especially if you're using the resin-based 3D stuff, which seems like it gets better fidelity. I don't know, I like the resin-based stuff. I also like the sort of spooled plastic stuff. They both got their pros and cons. I just think they'd be neat to tool around with, you know? 3D printed 3D model like claymation. that would be pretty. I actually thought about doing a Spaceman claymation sort of like over what would you call it? Overlay for the model. That'd be some next level investment. Yo, but here's the thing though. I was messing around with Live 2D because I'm working on the Spaceman 2.0 at the moment. And I was finding ways you can do like when I move around now, the tracking is very smooth because it interpolates a lot of the motion. Like really, we've only got like 9 or 12 set keyframes, and the rest is sort of motion tweened in between. But you can set it up where the values are much more snappy, I guess it would be, where it almost looks like more traditional animation, like frame by frame. You have to manually set a lot more frames, mind you, but you get it where, you know, you'd go from like here to here to here, like really snappy without all this smoothness in between. And I thought that would look really cool if you set it up with like a claymation sort of effect. Because you see all those like stop motion shorts and films and stuff like that done in claymation, and it's always sort of, you know, jittery. It's got that effect to it because it's all, you know, they move it slightly, they take a picture, move it another slightly bit, take another picture. I think it could work. Kind of bordering stop motion. Yeah, you can simulate that in Live 2D. You just got to manually set a lot more keyframes. Yeah. I wonder what we're gonna have to do for this one. All right. We get to use up to 4 nodes. We've got 2 input streams, which makes me think that the key to victory here is going to... Oh, but look at this. Look at this, though. This one can take only circles. This one can take only squares and triangles. This can take anything. We don't have to compare colors this time. All right, I already think I've got an idea for how this one's going to work. Can we get away with just using 2 perceptrons here? It might not be fast enough, but let's see. We would basically just want to double check this one. Or do we double check all of them? No, why would we double check all of them? Gotta run now, take it easy. Thanks for showing up, Dragon. Good chatting with you. Hope you have a great evening. And we'll see you again real soon, I'm sure. Tune in this Friday, you guys. We're gonna have Dragon back on the show for a little action. Until then, take care, sir. Fly safe. I mean, when you think about it, one of these streams we could just send straight into the output because it just takes everything, right? But it'd be overkill. Because we gotta have... Look, we gotta have 30... is this going to be another one that we have to cheese? Is this going to be the solution here? We got to have 30 in each of these. We've got enough to divide between here. Alright, let's see what happens then. Circles go up here. That should get some overflow. Because it's not 100% accurate. You shouldn't just be sending data from the input to output. Okay. Let's sort some data. Alright. We'll pretend that we're actually sorting. Here we go. Test run. We gotta keep above 70% accuracy here, that's the thing. See, it's just not getting fed data fast enough, that's a problem. We run out of time. Okay. So we are gonna have to rethink this then. Let's send all the circles up to here then. Then can we get away with just dividing the rest between the other two? Let's train it up and let's see how that goes. Good stuff, and let's test. Come on, surely we can get enough nodes of data in there within 30 seconds. Let's go, come on. 5, 4, 3, 2, we're just waiting on this one down here. That's the problem. Ran out of time. So we're not getting enough data to output stream 4 in time. And why would that be? We're getting enough into stream 2, it seems. So let's reroute data from stream 2 into stream 4. Let's see what happens then. Are we going to have enough in stream 2 in time? This was what I was worried about most, is that we'd fill up stream 0 in time. We definitely have. I trade some more here. Crisscrossing all over the place. We just got to get enough output into output stream 4 in the next 5 seconds. Man. Okay, okay. Tell you what. Maybe we don't need to send 2 streams of circles up here. Maybe... It's honestly sad when you think about what you were saying, where back in the day they told you to be more careful with... They told me that all the time! I took that to heart. Even today when I'm doing like little side projects and stuff like that. I'm always so conscious about, you know, proper documentation, about proper, you know, code efficiency. Nowadays people, you know, they'll just make up a billion variables, toss it, trash it, reuse stuff. What's the word for that? Redundancy. Too much redundancy. I feel that in today's world, everything needs to meet a deadline and everything's in a rush. I feel ya. What happened to elegant programming from a more civilized age? Alright, show me where we're at, and we'll start making changes here. Alright, I don't want this going down here, I want it going here. Or going here. Yes, definitely there. And you can go here. So I think output stream 0 is getting enough as is. Or it was, at least. Now we're hardly getting anything. Look at how slow output stream 4 is filling up. Tisk tisk. Revenant Novarik, is this Harbor Station music or is it from the game? No, this is straight from the game. Just a little jazzy background muzak, as it were. Surely designed to keep us from smashing our brains against the wall here. Let's cancel these connections. Let's rethink this through. This is going to be another gold medal victory where the only reason that we get it is because we've cheesed the system again. And as we've been saying with Mr. and Mrs. Pups, with Dragon who was here earlier, with everybody who's been tuning in, what a harsh lesson to try and teach players. That sometimes you gotta sacrifice accuracy and efficiency just to meet a quota. Or a deadline. I'm gonna have to start paying attention to what is coming out of these input streams, first, second, and third, and what have you, in order to get this right. Alright, if we send... If we send... circle, and... the triangle up there. That might be enough. Then we'll send squares, and circle has to go down here, so we'll do square down there as well, and triangles here. Let's see if this works. You can see we've already dipped below our 70% accuracy here, but as more circles show up, are we gonna get back over that line? We didn't even get it done in time. Man. All right, reset. Let's go with our first initial design. Circles go here. Those go there. Those go there. I think this got us a bronze victory. We've got room for 2 more perceptrons, so maybe... Launch failed. Maybe we're going to have to do some secondary comparisons here. Let's see. Let's find out. All right, so we're going to say circle. This is going to be our circle double checker. Circles go into here. Otherwise, these go here. These go here. And our overflow, right now we're going to put it in the trash, but it's not going to stay in the trash, because I'm sure eventually we're going to have to send it somewhere else. That's valuable data right there. It could jumpstart some of our other zones, some of our other outputs. Speed up, come on, let's go. And how you doing tonight, Revenant? Revenant and Novarik. Nice to see you again. I hope you had a nice weekend. I hope you had a good start to your week. All right, 30 seconds on the clock. So we're a little shy. Output stream 4 and output stream 0 by the time it all gets done. So we are going to send squares from here and triangles from there, because I'm pretty sure that'll be within our accuracy limits. Let's try that. Good, good. Keeping myself busy and distracted. That's the way to live. How is it on Harbor Station, Spaceman? I'll take a look to the sky next time you pass on by. Oh, thanks. Oh, look at that. We actually got it finished this time. Bronze Star. How close were we? I'm going to have to play that back. We're doing pretty good tonight. Doing pretty good. We're accepting no substitutes when it comes to this, this puzzle game here. We've got room for 1 more perceptron, so maybe what we should be doing is double checking both of these circle streams. Instead of sending them both into this one, I could be doing twice the processing at the same time. And then for argument's sake, let's say everything else goes to stream 4 for now. Let's train that up. Might have to change the direction of some of those. Just gotta sit through the formality of the training process here as we pretend that this is actual machine learning. Come on, let's go. And there we go. All right, give it a test run. All right, we have more nodes with which to process, with which to compare. 10 seconds. Let's slow this down here because I want to see how close we're getting by the time the time runs out. Okay. So we just need to speed up transfer to output stream 0. So let's send... You know what? Let's send squares up here. And we'll send the triangles down here. That should stick within our accuracy bounds. 3, 2... Okay, that's filled, that's filled. Ah, look at that though. We're still so close. Where else can we make changes here? We can send these triangles up here. That's slightly more. All right, give it another shot. Here we go. Testing and retesting. Nope, still too slow. All right then. We won't send the triangles up, we'll send... both triangles? No, the big square? Can we afford to give away the big square? We're gonna find out. We've got 35 of these. That's a lot of data to send through, or to sacrifice to output stream 0, but might be just what we need to tip us over the edge. 10, 9, 8, 7, 6, 5. Start to slow down here. Oh, yo, we did it! We did it! Look at that! Time spent 44 of 44 seconds, right on the line. Wow. Ship that. Can't do any better than that. Fantastic. All right, we got all those little tasks done. We got to move on to new concepts. RL0 or text recognition? What is RL0? Reinforcement learning. Hello, we is a society of peoples who love skits. We want our cats to has all the best. We want cats to... I don't know why I decided he sounded like that. Wants cats to drive cars with no humans inside. But cats have no hands, cats has paws. Can you make a car to drive to self-drive? Yours, Dr. Meow W. Cats, human person. Yes, please excuse the grammar. We are not cats, we are humans. But we can't type well because we have paws and no hands. Terrible car accident, bad surgery is why we need a self-driving cars. Haha. In reinforcement learning tasks, nodes work a bit different way. In a bit different way. All data is initially unspecified, and your task is to recognize it and transmit it to RL Agent, the AI. Oh, this sounds fun. All right, we've still got SIFT object detection, gets the unrecognized data on the input and classifies them as either an object or as a road. Objects go to the upper socket, roads to the bottom. In the real world, scale invariant feature transform is one of the most powerful non-neural algorithms for detecting features on pictures, which is essential for image recognition. Very fast, capable of recognizing simple objects and patterns. Man, we're learning so much stuff. All right, so we take the front LiDAR. And what? We pass it to here? That's the only input output that we have, is it not? Test run. What is it actually learning here, though? Test run complete. All right. Tune it on this screen. Ah, I see. You'll be training and testing your AI. AI acts basing on data you've been recognizing when building your scheme. The data about surroundings on the road are processed from your scheme to machine learning model. Your car won't be capable of learning and detecting obstacles without it. The goal in this type of task is to make the AI clever enough to be able to reach the target average speed level. Press supervised learning and drive the track yourself to teach the AI. Be careful, the car sees only objects inside a LiDAR area. Oh, wait, what are we supposed to be doing here? Am I slowing down? I'm slowing down. Oh, here we go. This is what we're doing, okay. Let's speed up. We move to the, there we go. Speeding up. There we go. Speeding up. Max speed, okay. Press training and watch the car's AI trying to reproduce your actions. We hope you've been driving safely in that supervised learning stage. Well, we'll see. What does it mean to evolve? Nope, that's not good. Your model has achieved the target speed level. Great, I guess. Press test and enjoy your results. If they aren't good enough, try training the car again. Do they know to move? Okay. No crashing yet. That's good. So far, so good. It's good to get out of the way in time. Hey, look at that. Knows to slow down. Hello, Vector, says Sleepy Siren TV. How you doing? Welcome to the show. Fantastic. We're just playing a little While True Learn tonight. Trying to teach us some basics of programming and machine learning. It's cool stuff. A little puzzle game. How are you doing tonight, Sleepy? Or do you prefer Siren? Do let us know. Thanks for tuning in tonight. I hope all is well. Hope you had a great weekend, a great start to your week. Do anything fun? Let us know about it. All right, looks like we did okay there, despite the fact that I wasn't really 100% sure what we were doing. Let's ship it. Sure, I'll take more cat cash from that. I'm good. I realized I've been following you but haven't watched a stream. Well, welcome to the show. I'm Vector Spaceman, your host of the Vector Spaceman Show. Kind of a lazy stream tonight. Not our most action-packed, but stuff that I'm at least a little interested in. This has actually been a really sweet game so far, especially if you love optimizing your performance. But I prefer Sleepy. I haven't done much as far as the week goes. Same. Same. Been talking to a few space cadets that have tuned in tonight. It seems like we've all had the same sort of experience. Slow start to the week. Oh, my goodness gracious. But here it comes. Here things are starting to pick up. Hi, broski. Hey, mana, you. Dropping in with a party. Hello, turtles. Welcome to the program. I'm Vector Spaceman, your host of this fantastic Vector Spaceman show. We're just chit-chatting with the space cadets here, playing a little While True Learn. Getting a little edutainment up in here. Learning about programming, learning about machine learning. The nerve of these people trying to get education up in our video games. What's that about? Hope everybody's doing well tonight. Tell us how that chess game went, because I know that's what you and Haster were just doing over on your stream, Manayu. Who ended up winning the mostest? Meanwhile, we've got new jobs to do here. Text recognition. We are aware that you were able to create a text recognition system based on the Rosenblatt perceptron. Yes, indeed we were. We need a similar system that would also be able to distinguish vowels from consonants. The task is simpler, but more accuracy is required. I love to be accurate. First perceptron machine was invented by Frank Rosenblatt. Look at us learning stuff. In 1957. Created the Mark I in 1960, a perceptron machine that can recognize English letters by their shapes. The very first, how you say, like text scanning sort of system, you know? The kind of thing that we use nowadays for, you know, text recognition, especially when we're doing archiving work and stuff like that. Oh, what's going on here? Oh, set. Set wants to be a VIP up in here. All right, we'll give it to you. We'll give it to you. Bada bing, bada boom, there you go, VIP. Good for the month of May. Only a week and change left, but I'll give it to you. Maybe we'll even let that roll over for you, Set. All right, we're supposed to be using one perceptron here. Taking our inputs. Okay, so we'll send circles up here. We'll send squares and such down there. Do a little bit of training. Let's go indeed. Got to sit through a short training period for the perceptron, get it up to speed. Yes, indeed, welcome, Raiders. I hope you all had fun watching Manayu's stream. If you all just came from watching her and Haster play chess, then you'll be in the proper mindset to watch a Spaceman try to do some visual programming. That looks like it'll break my brain. This is probably the easiest way to learn programming principles, is through visual coding, stuff like this. Let's give it a little test run here. We got to fill this up. We got to stay above 75% accuracy within the next 30 seconds. Are we going to get enough circles and triangles coming through here? Let's slow down so I can compare. Oh, look at that, gold star. All right. Not even a problem. Ship it. Should we work on parallel calculations next, or should we work on building a self-driving car? That sounds like more fun. Let's give that a try. Self-driving car. Hi, we are trying to launch our self-driving taxi service. It is a very promising startup, but we have a problem. Our algorithm makes a lot of errors when it tries to recognize traffic lights. As a result, the cars sometimes move instead of stopping. We hope you can solve this problem. The code must be working very fast. You're about to invest 4,000 cat euros in the startup. Are you sure you want to do this? Absolutely. Don't need to train your nodes while working on a startup. They already have the minimum error margin because time is money. I agree. All right, so we're allowed to use up to 50 nodes. That's crazy. I'm not sure we're going to need that many, though. We got to have 90% accuracy when it comes to triangles, though. So, in that case, maybe we want to use at least 2 of these. Maybe we want to use at least 3 of these. All right, inputs. We just funnel it like this. Just an extra stage. See, I can see some errors getting through, but we should stay pretty consistently above board here. Really, I guess a lot more got through than I was expecting. All right, stop this. We need an additional filter here, is what we need. And there we go, and oh! Joker Roxas VT has joined the Space Cadets. My goodness gracious, our latest and greatest Space Cadet. And you guys, check this out. If I'm not mistaken, as soon as that triggers, that's going to take us to our follower goals for the month of May. We hit it! 190 Space Cadets. Can you believe it? Thanks so much for tuning in. How you doing tonight, Joker? Thanks for following a little old spaceman. I hope you like what you see here tonight. Let's speed this up. As soon as we drain the input stream here, we'll be ready to launch. I'm pretty sure this is going to stay above board here. We've weeded out most of those errors. Yeah, there we go. Easily. Let's release. Deploys the code to the server. From this moment, the startup will work automatically. Let's launch. All right. Not always possible to satisfy all your customers in one day. Users with unfulfilled requests are shown in red color. Okay. You don't have the instruments to solve this problem for the startup, but you'll get some to handle the future ones. All right, making a little bank. Remember, we sunk 4,000 cat euros into this. All right, we're starting to lose money. All right, we got some more. Oh, look at that. Made all of our cash back almost. But server cost for the cat cloud. Can we make it a whole extra week before we cash out? Before we sell all of our money here? Let's see. That's pretty good. That's pretty good. And oh man. All right. As soon as this starts to decrease, that's when we're gonna beat it here. Oh, look at this. Look at this. Our stock just keeps rising. Okay, time to dip. Ooh, we made some cat moolah there, didn't we? Fantastic. All right, time to learn new tasks. Parallel calculations. Hello, we represent a scientific center. Our current programs are underperforming. This is terrible. This sounds like a job for the spaceman. Can you parallelize our calculations? I love to parallelize. To process data, your nodes need computing power, aka a server. Certain nodes require more than one server. The more servers you have, the more expensive your scheme becomes. Understood. So we're introducing load balancers now. This node routes elements to the least overloaded socket. Okay. See, I was seeing data getting backed up in a lot of earlier schemes. This will be helpful. Warning, this node requires additional server power. Gotcha. In the real world, a load balancer is a device that distributes network or application traffic across a cluster of servers. Load balancing improves responsiveness and increases the availability of applications. I love how they give you all of this extra stuff that you can learn from. It's fantastic. All right. So we got a balancer here. This is just teaching us how this works. It's going to send it to whatever is least overloaded. Look at that. Bing, bang, bosh. Now, what can we do to put it into practice? Sales predictions. Good afternoon. We just bought a stock of trees. Friends say that you can calculate the peak demand period. Please help us. I would love to help out. Okay, this is just tree color separators. Let's see. All right. But this has got to be 100% accurate? Just green. Surely that'll work, right? Give it a test run. Does that actually... Okay, so the any does work properly. As long as one color is selected for the other ones. As long as we're not splitting it like we have been before. Cache it, release it. Ancient artifact, hoo-hoo! Our group is working on finding an ancient artifact called the Tesseract. It is a very unstable element which radiates energy in different specters. Specters? Spectra? Specters, is that right? We have almost found out how to use its power to benefit humankind, but we need a smart algorithm, written by a spaceman, no doubt, that will separate and direct the flows of energy correctly. Revolution in energetics is just around the corner, my friend. All right. I'm excited. Let's get involved. Okay, we can use up to 3 nodes, which makes me think we're probably going to need a balancer, a decision tree, and a trash can. Or maybe a couple of decision trees. We'll find out. We'll find out soon. Okay, so we need 100% accuracy in all of these. So first of all, that's what we need the balancer for. The any load is going to send it to here or to here. After which, look at this. We got green, blue, blue, green. So if we just say red and green, the red blues will go here, the green blues will go here. But we can only have one of these coming out of the input stream. Alrighty, alrighty. To be fair, though, just because this is just saying it can take all 3, doesn't mean that it needs all 3. So, what we want to do, I think, is put the balancer first, then we're going to have 2 split decision trees. Red and blue will go down. We're going to have to look at how many each of these needs. This is how they always get me with these different tiers of metal here. Let's see. We know the balancer goes like this. We need red and blue, which means we also need green and blue. So basically the exact same thing. Crisscross. Crisscross. Let's test run this. Our accuracy is going to be 100% across the board, but are we going to finish it in time? We are. All right, that was incredibly surprising. Didn't think that was going to work first time, but all right, let's ship it. New production. Top of the morning to you from Zemiletto Outfits. We're trying to optimize our production lines, and we need a system that would distribute textile by material and send them to respective conveyors in equal amounts. We believe that you can nail this job, so we're looking forward to hearing back from you. Spaceman's on the case. Okay, we can use up to 4 nodes here. We got a shape tree. This can take any ore, so why not send it like this I'm not even sure I need anything but balancers here. Oh, but you know what? I do need a decision tree here. Squares go here, circles go here. Test it. I mean, I'm pretty sure that's going to be 100% accurate, but are we going to get everything through in time? Doesn't look like it. Slow down here so we can see everything in action. Now we're fighting just to get bronze completed. Might get that finished. Yeah, bronze? Nah, we can do better than bronze. Problem is, we gotta send more circles up top. Check this. Give it another test run. Doodle-a-doo. We could still make use of one more node here. And it looks like we're gonna have to. Look at how this is getting backed up here. Okay. Definitely not what we wanted then. Let's not use a decision tree there. Let's use another balancer. Let's send this stuff down below. Just go like that. Because this only needs, what, 28? That only needs 13. So what's that? 31, 41. Easily got enough there. That'll split it up even. Then we'll use decision trees here. Say anything can go. Or no, maybe we don't want to do that. If we say circles and squares, and this is going to send circles and triangles. This is going to say squares and triangles. That might work. Let's give it a go. Not really getting anything to output stream 1, unfortunately. We gotta speed up that output. Alright, we'll stop that. I think we're gonna have to put the balancer first. I mean, this down here, that's absolutely getting finished. Look how quick that goes. Zip. Look at that. That's gold star right there. It's just the top output streams that we need to worry about. Which is making me think, maybe, just maybe, what if we do this? Look at that. Do another test run. Do we actually have enough to fill that up? We do, okay. That's interesting. So now we've got 2 nodes to play with. All we have to do is get 15 squares or triangles into output stream 0. Or circles or triangles. My bad, my bad. Since we don't have any trash to work with, let's give that a go. should work, right? Come on, we're gonna be right at the... Yeah, there we go. Right on the line. Ship it. Fantastic, we've gold star everything that we've done. Man, we're so good at cat-based programming. What a bizarre statement. All right, large parallel calculations. Our parallelization system broke after the last Doors OS. Not Windows, but Doors. Get it, get it, get it. Can you fix it? It's a very big system. Be careful. Oh, I'm sure we can do this. The darkest years of machine learning. Oh, we're getting a bit of lore here. In 1969, Seymour Papert and Marvin Lee Minsky wrote a book called Perceptrons. In this book, they spoke about math constraints of the first perceptrons, which were just XOR problems. This book has shifted the scientific interest and funds toward distribution from the U.S. government organizations, slowing down the progression of machine learning for almost 30 years. Oh, my goodness. The expanded version of the book was released in 1987, containing chapters that disproved the statements from the critical remarks made since 1969. Goodness gracious. Doors. Yeah, get it? You see what they did there? You see what they did there? All right, we got 10 seconds here to reroute our squares. It's just going to be a case of doing something like this. Each one of them needs 8. So just proper distribution. Give it a test run. Doodle-doodle-doodle-doot. 5, 4, 3 is going to be right on the line. Yeah, there we go. Ship it. Large parallel calculations. Secret information. I love secret information. Good day to you. We are a secret military organization. Our code name is Protoss. Do you think they need more pylons? Do you think that's what it is? Everything you are going to read further is classified. Our analysts are sending operatives to various war zones. An escalation of conflict with the enemy has recently occurred. We are in need of self-learning algorithm capable of sending dedicated units to respective parts of the battlefield. Like warping in, perhaps? That 100% sounds like a StarCraft reference. Alright, we can use 3 nodes here. We have a selection of 4 different nodes to choose from, though. We've got the balancer, decision tree, color, trash can, and we've got an expert system here. So, how to optimize? I think a balancer is due. We gotta get 30 units of data up in here. So I think maybe the first thing we do is not balance, but set up a color tree. So we want red distinguished and green distinguished, because that'll send through green and blue. This will send through red and blue. Is that really... I would love to isolate red, though. So we'll do that. Green and blue can just go down here. Blue, red, gets split like this. Give it a test run. Oh, you know what? I did not set up the input. There we go. Give it another test run. All right, the data is flowing. I don't feel like we're going to get this filled up in 90 seconds, though. Why is it so slow to come out at this point? Are we even going to make bronze? We made bronze, but come on, we can do better than that. All right, what happens if we balance first? It's not going to be 100% accurate, but let's give it a shot. Look at how fast it flows. Problem is, we're missing accuracy here, we're missing capacity there. But I guess that balancer comes through first. I don't know, is packet momentum a thing here? It sort of feels like it. All right, here's where we'll put in a color tree. Any color can go down below. But red has to get balanced again. Give that one a test. There it goes. Man, we got nothing left over for up here. Why is that? Is red getting sent down here? It is. We're losing red. We're filtering through here. Okay, in that case... what do we want to do? The balancers are so fast. Green and blue, red and blue. That will appropriately split it. But I'm just not sure it's fast enough. Here we go. See? There's our problem. We've run out of stuff again. Why is that? Hold on. Stop this. Restart. Where are we? Ah, because we're splitting some down here already. We're losing half of our reds. I have been muted. You're absolutely right, Rabbit. That's rough. That's rough. Just been talking to myself most of the time anyways, though. But good catch. Alright. We can solve our capacity problem at the cost of our accuracy. We can see here by using two balancers. To split the load, it allocates everything with such speed, such efficiency. Now we just got to color correct. And to that end, let's see. We're given 27 seconds for this whole thing to work. So you would think that since this only takes 0.3 seconds to make a comparison, that we would be able to say red and blue or how about just reds and then anything else gets sent down below. We should be getting enough, I think. Send it, let's see. But nope, not nearly enough actually. Because it's sent, oh, of course, because it's sending a lot of the reds down the any path. So we want to do this then. Green and blues go down here, reds and blues go up here. That should allow us to keep a few more of them, because now we'll get reds and blues up top. But it still doesn't look like it's enough. We finished comparing everything by the time the time runs out. That's great. So maybe the decision tree comes earlier. Not too early, perhaps, but what if we put it in the middle here? Go like this. We say reds and blues. So what do we have here? Half our reds get sent up here. Presumably. So they can go here. Greens and blues can go down here. I feel like we've had this setup before. Oh, hold on. Hey, gold star, look at that. We must not have. And look at that, we only had to use 2 nodes. Bam, ship it. Cyber Initiative. How long have we been going here? This might be our last one for the evening. Before we'll start next time up with a task called Dictatorship. But this one's called Cyber Initiative. Greetings. Our company, Cyber Initiative, is into manufacturing androids. Our production lines are fully robotized. The only function which is still performed by human workers is logistics, i.e. us. We're shipping and We're shipping our androids to the government, military companies, etc. We would like to automate this process with an algorithm that will distribute androids depending on their characteristics. Glory to the robots, of course. Yeah, start with the one called dictatorship, not sketch at all. Yeah, nothing odd about that. Spaceman learning how to think like a machine. Suddenly things change. Glory to the robots, you guys. Alright, what do we got to do here? We can use up to 7 nodes. This one could be intense. Alright, we've got expert systems, decision trees, trash cans, balancers. We gotta have enough reds. 27 reds. So, that's telling me that we got 36 seconds to compare everything. So, these all have to be 100% accurate. So we'll do a little color tree action here. Put in a backdoor for future sabotage. That's right, a little exhaust port. So do red and blue, that's fine. So we can siphon off red and green here. Or no, here we'll do a red and green, red and blue, because we can use the offshoots to fill up this down here. Or what else could we do here? We could say, so we're gonna get about 20 red. We're gonna have to have a color filter up top too, aren't we? Huh. Alright, let's say we're getting 20 reds down at the bottom. So we'll say, yeah, fine, we can use this for the moment. Red and blue feeds into this. The red goes here, the blue goes there. The green and blue. Just feed it up top here, I suppose. Because the other half, we are going to have to send some more red again, unfortunately. So we're going to have to split this again. Then a red-green split. The red feeds into here. The green and blue, we can feed it into here like we did before. Then we can probably balance the rest out like this. Let's give that a test run, see how it run. Okay, slow it down, slow it down. All right, we've run out of data. So what have we done? We're still short in output stream 1 and output stream 4. Okay, so how can we fix that? We'll send this here instead of to output stream 0. Oh, did we make it? Okay, we made that. And so we're just short on output stream 4. We've got more than enough time. So we just need to split off some more blues here. Oh, because hold on. Oh no, that is feeding. All right. Blue goes here. Blue's going down here where it belongs. We'll use another color divider then. Going red to red and blue. This is green, so let's set up a green and blue. Send the blue down here. We'll send the green right here where I believe it was before. Let the data flow. Okay, and there we go. Success. Easier than I thought. And look how on the money this all is. Fantastic. We did it, you guys. We aced another section, by the look of it. So the next thing we get into will be dictatorship, whatever that's about. That sounds like fun. That sounds right up our alley, don't you think? Well, let's get ready to close things out. Why don't we? Let's head on back to the main screen here. Ah, another fantastic evening of coding, or visual coding facsimiles. Hope you guys had an alright time tonight. Maybe you learned a thing or two, who knows? Before we close things out, though, we'll just take a quick peek at who's working tonight. Maybe we'll go say hello to some friends of the show, huh? Oh, I know who we're gonna go see. Let's go see Madame Cory Ojo. You know, she's got a special stream coming up this weekend, this Saturday. Hope you guys are gonna tune in for that. New album reveal, new model reveals, all sorts of fun stuff. Thanks for the stream, Spaceman. Hey, thanks for tuning in, pups, Mr. and Mrs. And of course, to Revenant Novarik and to Dragon Durant and to everybody else, and of course our latest and greatest Space Cadets, Joker, and to Mana Yu for bringing the raid in with all of the peeps. Have a great rest of your night and hope you learned a lot. Whether or not we learned a lot, we had a good time. I think that's what's more important, don't you? And of course, everybody who stays lurking in the chat, you know we appreciate each and every one of you. Let me set up that raid here. And we'll get ready to close out the show. All right, Space Cadets. Without further ado, let's close things out. Let's say goodbye. Let's go and have ourselves a nice night's rest, shall we? Space Cadets, everybody who showed up tonight, new and old, I want to thank you all for tuning in today, wherever and whenever you are. Now you can join us again on Thursday, same time, same place, live at 8 p.m. Eastern, right here at Harbor Station. We'll catch you on the other side, Space Cadets. Until then, of course, no matter what life throws your way, good luck and Godspeed. This is Vector Spaceman, signing off. Now stick around for that raid, because we're about to send you off for some more great content for your evening. Take care, everybody, and we'll see you again real soon.